Last day, what we did is an introduction to the Haskell system that we'll be using in this course, which is the Glasgow Haskell compiler, or GHC for short. And we also looked at running your first Haskell program. So what we're going to be doing today is looking at types and classes, which, as we'll see, are two of the fundamental and most important ideas in programming in Haskell. So we're going to start off with a question, and the question is, what actually is a type? And it turns out this is actually quite a difficult question. There are people who spend their entire lives thinking about this question, and they're called type theorists. And we actually have a few of these in Nottingham. But for us in this course, we're just going to have a very simple and very easy answer to this question. So for us, a type is simply going to be a name for a collection of related values. So a type is simply a name for a collection of related values. So a simple example of this would be in Haskell, the basic type bool, which stands for Booleans, contains the two logical values false and true. So that's what a type is. Then we can think, well, what actually is the point of types? Well, there's many answers to this question, but for us in this course, the primary answer is that types are going to be about detecting errors in your programs. So the idea here is that when you apply a function to one or more arguments of the wrong type, that's going to be called a type error. So here's a simple example of this. What I've done is started up GHCI, and I've got the little greater than prompt, and I've tried to enter an expression, and it's given me an error, and in fact it will give me a type error. So what's gone wrong here is that I've tried to add things which you cannot add. So in particular, 1 is a number, and false is a logical value, but when you try and add them together, you require 2 numbers. So we're going to get a type error. So what I'd like to do for the next couple of slides is explain to you how types work in Haskell. So the first point here is a bit of notation. So the idea here is if I give you an expression e, and if you were to evaluate it and it would produce a value of type t, then we say that e has type t, and we write that as in the blue box. We say e double colon t. So whenever I write down e double colon t, it means e is an expression. If you were to evaluate it, it would produce a value of type t. Okay, so that's the syntax we're going to be using for types throughout the whole course. We'll be writing dozens and dozens of types like this type signatures like this every day. Then a nice thing about Haskell is the second bullet point here. So every well-formed expression has a type, and it can be automatically calculated at compile time using a process called type inference. So you don't need to worry about writing down types because the system can calculate them automatically for you. But in fact, it's always a good process, it's always a good practice rather, to write down the types of top-level things, because as we'll see as we go through the course, that's really going to help us to define things, and it will also form some useful documentation for our programs. But in principle, you don't need to write down the type of anything because the type inference system can calculate the type of any expression in the language. The next point to note is that all type errors are found at compile time in Haskell, which means that Haskell is so-called a strongly typed language. And this makes programs safer and faster by removing the need for type checks at runtime. So in particular, it makes them safer because you can't actually get any type errors at runtime, and it makes them faster because you don't need to go to the labor of checking if any type errors happen at runtime, because they can't. They're all found at compile time because Haskell is a strongly typed programming language. And the last thing here is a little useful GHCI command, which we've already seen. It's called :type, and it simply calculates the type of any expression without evaluating it. So this point is brought home by these two examples here. So in the first example, what we're doing is asking the system to evaluate not false. So not is a function. It takes a logical value as an input and just flips it. So it flips false to true and true to false. So here we've just applied not to false. So it will evaluate that by applying the function, and we'll get back the result true. In the second example here, we're asking the system not to evaluate not false, but rather to just work out what its type is. So we say :type and then not false, and what this will do is it will invoke the type inference system, and it will look at the structure of what we've written there, and without evaluating it, it doesn't cheat, it just looks at the structure of it, it will work out that this is a Boolean. And this is very easy in this case to do, because false is a Boolean, that's a logical value. Not is a function which takes a Boolean as an input and gives a Boolean as an output. So without evaluating this, we can actually just look at the structure at it, or rather the type inference system will look at the structure of it and figure out that it is a bool. So the type command, :type, is very useful in this course. So what we're going to be looking at now for a while is the basic type system of Haskell. And we're going to kick things off by looking at the basic types. So every programming language has some built-in types, and Haskell is no exception. There's dozens of them, but for the purposes of this course, we're only going to be needing a few very basic types, and these are the ones we're going to be using here. So first of all, we have bool, which is the simple logical values true and false. We've already seen these. We've also have the character data type, char, and this comprises single characters enclosed in single quotes. Remember, back quotes are used for making functions with two parameters into infix operators. We've seen that last time around. We also have the type of strings, so that's just sequences of characters, and you enclose those in double quotes, as you do in many languages. We have the type int for integers. These are 64-bit integers. And we also have the type float for floating point numbers. And we have other things like doubles and so on. But to be honest, most of the types that we'll be using in this course will be the first four here. From time to time, we'll use floats, but not very often. So what I want to show you now is three fundamental ways to form new types. And these will be lists, tuples, and functions. So first of all, let's have a look at lists. So a list is simply a sequence of values of the same type. And we've seen many examples of lists in the course so far, so we know the syntax. Lists are enclosed in square brackets, and then you have a bunch of things inside, and you separate them by commas. So here's a couple of examples of this. I have the list false, true, false, and that has type using the double colon operator, list of bool. And the second example is I have a list of characters, A, B, and C, and that just has type list of char, exactly as you'd expect. And in general, if I give you any old type T and I write square brackets around it, that's going to be the type of lists with elements of type T. And an important point here is that there's no constraints on this type T. It could be anything you like. You could have lists of lists, you could have lists of tuples, you could have lists of functions, you can have whatever you like. So just a couple of quick points to note about the list type before we move on. So the first point here is that the type of a list doesn't tell you anything about its length. It doesn't tell you how many elements are in it. So this is illustrated by these two examples here in the top blue box. So in the first example, I have the list false, true, and that is a list of bool, has type list bool. And in the second example, I have false, true, false. I have 3 booleans, and that has the same type. So if I covered up the values here, if I covered up the lists and we just looked at the types, in both cases we have a list of booleans. So all we know is that we have a list and that the elements are Booleans, but we don't know what they are, and we don't know how many elements there are. So the types are kind of telling you something abstract, telling you something about the structure of the value, but not everything. And we've already made the second point here. The type of the elements is unrestricted. So for example, we could have a list of lists. So we see this in the example here. So I've got two lists here. I've got the list comprising the character A, and that is a list of char. And then I've got another list comprising two characters, B and C, and that's also a list of characters. And then what I've done is I've put them within another list by the outer square brackets, and that gives me a list of characters. So we have a nested list, and you could nest this as many times as you liked. So this brings us on now to tuple types. So a tuple is simply a sequence of values of possibly different types. So they don't necessarily have to have the same type. So a couple of examples here. Here we have the pair, false and true, and that has type pair of Booleans. So you can see the syntax for tupling here. You use round brackets. And a tuple is just a kind of generic term for things like pairing, tripling, quadrupling, and so on. So it's something that you're already very familiar with from kind of high school maths. So the first example, we just have a pair. We don't have different types here. We have two Booleans, false and true. The second example illustrates that you can have different types here. So in this example, we have a triple comprising a single Boolean, false, then a character A, and then the Boolean true. So this is a triple, so it has type, the triple bool, char, bool in round brackets. Okay, so the basic idea here is very simple. So the general case is a bit of a mouthful, but I'll go through it. So it says brackets T1, T2 up to Tn is the type of n tuples whose ith component have type Ti for any I in the range. Okay, so a bit of a mouthful, but the general idea is very straightforward. A tuple is just a sequence of values of possibly different types, and we use round brackets for tuples, whereas we use square brackets for lists. So a couple of things to note about tuple types. So the first point is that the type of a tuple tells you how many things are in it. It encodes its size, and it also tells you exactly what type the things are as well. So look at these two examples here. So here we have a pair comprising false and true, and it has type pair of Booleans. And then we have a triple comprising false, true, and false, and this is a triple of Booleans, bool, bool, bool. And this is in contrast if we look back to the same example here. Here we had a list with false and true, and a list with false, true, and false, and we see that they had the same type. They both had type list of bool. Whereas, when we look at the tuple type, we see exactly how many components. If we covered up the actual tuples and just looked at the types, we see in the first example we have a pair of Booleans, and in the second we have 3 Booleans. Okay, so the tuple type tells you more information. It tells you how many things you've got and exactly what each of the components or each of the elements are. And again, the type of the components in a tuple is completely unrestricted. You could have tuples of tuples, you could have tuples of lists, tuples of functions, you can have whatever you like. So here's a couple of examples of this. So in the first example, I have a nested pair. So we have a pair whose first component is the character A, and whose second component is also a pair. And that pair is comprises a false and a single character A. So what we have here is a nested tuple. The first thing is a char, and the second thing is itself a pair of a bool and a char, and that's reflected in the type on the right-hand side. So notice that the structure of the tuple is reflected exactly in the structure of its type. Then we have another example, which is a pair, which contains a list as a component. So the first component of the pair at the bottom of the slide is true, so that's a bool, and the second component is a list, and that's a list of char. So the type of this pair is it's a pair of a bool and a list of char. So this is basically all you need to know about tuples. So now we move on to the most important way of forming new types, and that's function types, because Haskell is a functional programming language, so our programs are mathematical functions. So a function is a mapping from values of one type to values of another type. So here's a couple of simple examples of this. So first of all, we have the not function, which is the negation function on Booleans, and it takes a single Boolean as an input, and it gives a single Boolean as an output, and it simply just flips them. So if you give it false as an input, it will give you back true, and if you give it true as an input, it will give you back false. So its type simply says not has type, so double colon, bool, arrow, bool. Takes a bool as an input and gives you a bool as an output. And even is a library function as well. It has type int bool, and it simply takes an integer as an input, and it gives back true if it's an even number, and it gives back false otherwise. So this is called a property or a predicate. In general, functions which return booleans are called properties or predicates. And the general case is very straightforward. If I give you any old types, t1 and t2, then t1 arrow t2 is the type of functions that map values of type t1 into values of type t2. And again, there's no constraints on what t2 and t1 and t2 could be. They could be anything you like. They could be tuples, they could be pairs, triples, and so on. They could be lists. They could even be functions. And we'll see in examples of this in a minute. Another point to note here is that function types only have one input type, like t1, and one output type, like t2. But what we'll see is the flexibility of the Haskell type system means that even just having functions with one input type and one output type already means that we have the power to define functions with multiple arguments. So a couple of little points to note here. So the first point to note is that the arrow, which is the kind of mathematical function arrow, is typed at the keyboard as a minus sign followed by a greater than sign. So I quite like to use the mathematical symbols for various things in this course, but all of them can be typed on a keyboard in a kind of obvious way like this. And the second point kind of calls back to what we were just thinking about. So the argument and result types are unrestricted for a function. So this means, for example, functions with multiple arguments or multiple results are possible by the idea of passing in or returning lists or tuples. So let's have a couple of examples of this. So the first example here is a simple addition function. So the type says add has type pair of integers to an int. So it takes two integers and gives me back a single int. And note here, I didn't actually need to give this type declaration here because the type inference system could work that out behind the scenes for me, but it's good practice in Haskell always to write down the type of things that you define. And I will always be doing this in this course, and I suggest that you do too. And then the definition for the add function, which is the equation, is exactly what you'd expect. It's just kind of high school maths type stuff. It says if we add a pair x comma y, we simply get back x plus y. So this example illustrates that you don't need to have a special function type for functions with more than one input. You could just pass in a pair or a triple or a list or whatever you like. And we'll see many, many examples of that in the course. So the second example here shows that you can also return multiple results, and here we're actually returning a list as a result, and I've defined a little function called 0to, and it takes a single integer as a parameter and it gives you back a list of integers. And all it's going to do is take the number n in, and it's going to build the list from 0 up to n. So dot dot is a little library function which simply takes two numbers and builds the list between those two numbers. Okay, so what we're going to look at now is the idea of curried functions, which sound a bit spicy because, well, they are, and they're one of the key ideas in a language like Haskell. So the idea is this. So functions with multiple arguments are also possible by another idea. And the other idea is the idea of returning functions as results. So let's have a simple example of this. So what we saw a couple of minutes ago, or very shortly ago, is how to define an addition function which takes two numbers as a pair. Here's an alternative way to define an addition function using the idea of returning functions as results. So let's look at the two lines in the blue box here. So I'm defining a function called add prime. So I've given it a different name so that I can compare it with the other add function that takes a pair. And what add prime does is it takes a single integer as input. So we have the type int arrow there at the start. And then the return type is interesting. So the return type is actually a function. And what that function is going to do is take the second integer that you want to add, and then it's going to give you back the final result. Okay, so add prime is returning a function as a result. So it takes the first integer as an input, and then it gives you back a function. And that function is going to take the second number, and then it's going to give you back the result of actually performing the addition. So what you see here is that the add prime function is kind of taking its two parameters one at a time. Whereas with the add function here, we took the two parameters at the same time. We took a pair x and y. Here you take one number as the first parameter, and then you get back a function which expects the second one. So how do you actually write a definition in this form? So what I've done here is written add prime and then x and y with no brackets anymore, because we take the parameters one at a time now, and then we simply get back x plus y. Okay, so this is the idea of returning or building a function with multiple arguments by the clever idea of returning functions as results. So what's actually going on here, kind of under the hood, is explained in the callout box here. So add prime takes an integer x and it returns a function, add prime of x. And that function is waiting on the second input. Can't do anything yet. So this function takes another integer called y, and then it's finally going to compute the result, x plus y. So this is the idea of building a function with multiple arguments by returning a function as a result. So there's a couple of points to note here. So the first one is that add and add prime produce the same final result, but they do so in a different way, or they take their arguments in a different way rather. So in particular, add takes two arguments at the same time, packaged up as a pair, and you can see that reflected in its type in the blue box here. Add takes a pair of integers as its parameter. Whereas the add prime function takes them one at a time. It takes a single integer and then gives you back, as a result, a function which is taking the second integer. Okay, so they produce the same result, but they take their parameters in a different way. And the terminology here is functions that take their arguments one at a time by using this trick of returning functions as results. These are called curried functions, and this celebrates the work of Haskell Curry, who was one of the original people who worked on these things. And Haskell Curry is also the guy who gives his name to the Haskell programming language. So you can gives his name to the Haskell programming language. So you can play the same trick with functions with more than two arguments as well. So here's an example of this. I'm defining a multiply function which takes three parameters, x, y, and z, and simply multiplies them up. So I write mult x, y, z with spaces, no brackets because there's no tupling, there's no triple. Here we take the parameters one at a time, and then we return the result x times y times z. And you can see what's going on by looking at the type. Mult has type, then we have everything on the right hand side with all the arrows. So let's understand it. We take in an integer and we get back a function. And that function then takes in another integer and gives back a function. And that function takes in a third integer and gives you back the final integer result. And again, more precisely what's going on is explained in the box here. So the mult function takes an integer x and returns a function mult x. And that's kind of suspended, waiting on the remaining parameters. And then you take the next integer parameter y, and then you get back a function mult xy. And then finally that function is going to take an integer z and then return the result x times y times z. So this is the idea of curried functions. So now you can ask yourself, why are curried functions actually useful? So one answer to this question, we'll see a bunch of answers in this course. Curried functions are a bit more flexible than functions on tuples because you can often make useful functions by partially applying them. So for example, if I consider the add function, which takes a pair, I have to give it two things because it takes a pair as its input. I can't just give it one thing, I have to give it a pair. Whereas the add prime function, it took two numbers one at a time, so I could potentially apply it to just one number and get a useful function back. And this is the idea about why if you partially apply, as it's called, a function, a curried function, you may get a useful function back. So here's three little examples of this. So I could take the add prime function and apply it to a single argument. Let's just apply it to 1. And then that will have type int to int because it's still waiting on its second parameter. And what this function will do is when you eventually give it a second parameter, like 2, it will add 1 onto it and then you'll get back 3. So what you see is the add 1, the partially applied version of the add function, is simply going to increment whatever number you give it. So that's a useful little function. The last two illustrate something to do with lists. So take is a library function which has two parameters. It's a curried function. It takes two parameters one at a time. It takes an integer like 5 and then it takes a list and it gives you back that many elements off the start of the list. So in this case, take 5 would be the function that takes a list as an input and then it's going to give you back the first 5 things off the list. And then drop does this, kind of the opposite of that. It's going to drop the first 5 elements off any old list. So there's a couple of things you need to know about curried functions. So I'll call these curry conventions. And the first one is to do with brackets. So to avoid excess brackets, or if you want to be fancy, you could call these parentheses. To avoid excess brackets when you're using curried functions, there's two simple conventions. So the first convention is that the arrow brackets to the right. So we can see this in the blue box here. So here's an example Haskell type, int to int to int to int. So this is a curried function that takes 3 parameters, one at a time. And I haven't written any brackets in here, and almost all of the time when people write down function types in Haskell for curried functions, they don't put the brackets in. So this would be a function that took 3 integers, one at a time, and then gave back a single integer. But what it really means is bracketing to the right. So in the callout box down the bottom, really what we're doing here is we're taking in a single integer and we're getting back a function which expects the remaining arguments. So we can then take the next argument and we get back a function which expects the third argument, and then finally we get the final result. So remember, when you're writing down function types, we usually don't put the brackets in like this, and we just use the fact that the arrow associates to the right. So you see loads of types like that. If you look in the standard library, which I've given you on the web page for the module, almost all the functions are curried functions there if they take multiple arguments, and there won't be brackets written around things to show that they're actually returning functions as results. We just write kind of int to int to int to int, stuff like that. As a consequence, because the arrow brackets to the right, function application brackets to the left. And I'll leave it as a little puzzle for you to figure this out, why this is the case. If this brackets that way, then function application must go the other way. So it goes to the left. So when we write down something like mult x, y, z with no brackets, just spacing out the arguments, what it really means is bracketing everything to the left. So we apply multiply to x, and that will give us a function. Then we apply that to y, that will give us another function, and then we apply that to z, and then we're done. And the point at the bottom here says, unless tupling is explicitly required, all functions in Haskell are normally defined in curried form. And again, if you look in the standard library, basically almost every single function is defined in curried form. So one thing we're going to look at next time around, when we come to look at different ways to define functions, is I'm going to show you a little bit about the lambda calculus. And when we look at the lambda calculus, that will give us an alternative way, and actually a better way, of understanding what curried functions actually do. So we'll be coming back to curried functions again next time around. So just to wrap things up today, what I want to do is look at So just to wrap things up today, what I want to do is look at two special kind of functions. And the first of these is called polymorphic functions, and the second is called overloaded functions. So the definition here at the top of the slide says, a function is going to be called polymorphic, which means of many forms, if its type contains one or more type variables. So this sounds a bit fancy, but it's actually a very simple idea in practice. So let's have a look at the type of the length function. So what length does in Haskell is you give it a list and it just calculates how many things are in it. And it's polymorphic because it doesn't care whether you give it a list of integers or a list of booleans or a list of functions or a list of whatever. And this is reflected in the type by having a little type variable. And the type variable is the a here. So what the type means is for any type A, length takes a list of values of type A and returns an integer. So the little a there is a type variable. You can think of it as being a placeholder for any type that you like. You could fill in int there, bool, whatever you like. So this is illustrated with the examples here. So type variables can be instantiated to different types in different circumstances. So in the first example here, I'm taking the length of a list false and true, which contains booleans. So behind the scenes, the a would be instantiated to bool, and you get back the result 2. And the second example here is I'm calculating the length of a list of integers. So that's fine. Behind the scenes, it would get instantiated, and we get the result 4. So just a tiny little note at the bottom here, a requirement, not a convention. You have to do this. Type variables must begin with a lowercase letter, and we usually, to keep our program short or to keep our types short, we usually name them very simple things such as A, B, and C, etc. Okay, so I mentioned previously types themselves, things like bool, int, char, and so on, these begin with a capital letter always. You can see them in the call out boxes there. But type variables must begin with a lowercase letter, and we usually keep them very short, just A, B's, and C's, and stuff like that. An interesting observation is that many, if not most, of the functions in the standard prelude or the standard library are polymorphic, and here's a few examples. So the first of these is FST, which just stands for first. It's an abbreviation of first, and you can kind of guess what it does just by looking at its type. So FST has type pair of AB, so it takes an A thing and a B thing, and then it gives you back an A thing. And it does exactly what its type and its name suggests. Takes a pair of things, maybe takes an integer and a boolean, and gives you back the first thing, gives you back the integer. Okay, very straightforward. Head is one of the most commonly used library functions on lists. It takes a list of things and gives you back the first thing, so it takes a list of A and gives you back a single A. Take is a curried function. We've seen it today, and I think also previously. Take takes two parameters, one at a time, takes an integer like 5, takes a list of things, and then it's going to consume and give you back that many integers off the start of the list. So again, it's a polymorphic function, and in fact a curried function as well. So the next one is interesting. This is a function called zip, and let's look at its type. It's a curried function. It takes a list of A things and a list of B things separately, and then it gives you a list of pairs of A's and B's. And you can have a good guess at what this function actually does just by looking at its type. what it actually does is pairs up the corresponding elements from two lists. So if I give it a list of characters and a list of numbers, for example, it would pair the first character with the first number, the second character with the second number, and so on and so on. So it's kind of like a zipper. It's taking a list of one thing and a list of another thing, potentially different things, and it's just pairing up the corresponding elements. So it's a very commonly used function. We'll see some examples of this later on in the course. So the last one here is simply the identity function. That's an old friend from mathematics. It doesn't do anything. You just give it something and it copies it. Okay, so it goes from A to A. So the last thing we're going to look at today is the idea of an overloaded function. And the idea is that a polymorphic function is going to be called overloaded if its type contains one or more class constraints. So in the blue box here, we have a simple example of this. This is the type for the addition function in Haskell, and I haven't hidden anything from you here at all. This is the exact type of the addition function as you'll find it in the standard library. So let's understand what's going on with the type. So we say that the plus operator has type, and then we have a bunch of stuff. So the first part here, num_a, that's simply saying that the a type must be a numeric type like integer or float or something like that, because addition only makes sense for numeric types. And then we have a fat arrow, which is an equal sign followed by a greater than sign. And then we have the real type of the function, which takes two a's and then gives back a single a. So it's a curried function. It takes two numeric values of type A and gives you back a single numeric value of type A. So if you want to say this more concisely, that's in the callout box at the bottom. What the type expresses is for any numeric type A, the addition operator takes two values of type A and returns a single value of type A. So this is the idea of class constraints. num_a is called a class constraint. So a few points to note here as usual. So the constraint type variables can be instantiated to any types that satisfy the constraints. So for example, we could add two integers together. That's quite okay. We could add two floats together. That's quite okay. But we couldn't add two characters together because characters in Haskell are not a numeric type. Some languages let you add characters. Haskell doesn't. It tries to keep your programs safe so you don't have bugs in them. So char is not numeric, so you will get a type error in this case. So Haskell has a number of classes, a number of type classes. It's got lots of them. The three main ones that you'll come across in this course are shown here. So you have num, which is numeric types. You have eq, which is equality types, and you have ord, which is ordered types. And what these basic class constraints mean is kind of illustrated by these three simple examples. So we've already seen the first one. Addition for any numeric type A takes two A things and gives you an A thing. So we've already seen that one. The double equals in the second example, this is Haskell's equality operator. So a single equal sign in Haskell is used for defining functions. If you want to test if two values are equal, maybe if two integers are equal or two lists are equal, then you use a double equal symbol. And the type for double equal said, provided the type supports equality, because not every type does. You can check if numbers are equal, but for example, you can't check in general if functions are equal. So functions are not an equality type. Then you take two A things and you get back a true or a false, depending on whether they're equal or not. So that's the key function, which is in the equality class. The ord class is types which have an ordering on them, so you can check if one thing is smaller than another. So for example, integers are ordered just in the normal way, so 1 is less than 2, for example. So the less than operator says for any ordered type A, or any type that supports an ordering, then you have a function, a curried function that takes two A's and gives you back false or true depending on whether one thing is smaller than another thing. So these are the three main classes which you'll come across in this course. So just before we move on to the exercises, a few quick hints and tips. So the first one is, when you're defining a new function in Haskell, it's useful to begin by writing down its type. Okay, so rather than just going straight ahead and writing down a function definition, figure out what its type is first. And this is useful because once you know the type, then that will help you to define the functions. And we'll see many, many examples of this idea of types helping you to define functions in this course. The second point is, within one of your Haskell scripts, it's good practice to state the type of every new function that you define. So you don't need to do this because the type inference system can calculate it for you, but it's good practice to do it so that when you're reading your programs later on, you can kind of get an idea of what the function does just from looking at its type. And also, the type inference system will check, it won't trust you, it will calculate the type itself, and it will check whether what you've written down is compatible with what it thinks the type is. So it's kind of double level of checking there. And the last point is a kind of gotcha. When you're writing down the types of polymorphic functions, so that's functions whose types have some variables in them, the little a, b's, and c's, if you use numbers, equality, or orderings, you're going to need to put some class constraints in your types. Otherwise, the system will complain. But if you get stuck on this last point, you can always just define your function and then ask the Haskell system using the :type command to figure out the type for you and then just paste it into your script. So as usual, we're going to wrap things up by a few exercises. So basically in these exercises, you'll be playing the role of the type inference system. So in the first exercise, I've given you a bunch of values of increasing complexity, and you've got to try and figure out what are the types of these things. And again, they start off very simple, and the ones down the bottom get a little bit more tricky. In the second exercise, I've given you the same kind of problem, but this time you're going to be looking at function definitions, and you'll be playing the role of the Haskell type inference system and trying to figure out what the type of each of these functions is. And again, they start off quite simple, and down the bottom they get a bit more tricky. And then finally, you can check your answers in GHCI to see if you're right. And in fact, you can use GHCI to cheat if you want, which I'm sure you don't want to. You can type in any of these function definitions and say :type, then the name of the function, and it will give you back what the type actually is. So if you're watching this video on your own, you may want to pause at this point and try some of these exercises for yourself before I move onto my iPad and show you how to solve some of them. So we'll start off by looking at exercise 1, where you have to work out the type of these 5 simple expressions. And these are all fairly easy. Basically, all that you're going to do is a tuple, and we can write down the type for this list. Component is a list of characters. So again, nice and easy. So the last one of these exercises is interesting here. What we have is you can put any old thing, like a list into a list, as long as second, first few have the same. Type. So then we can move to exercise 2, and I'm not going to call it X's, that what we're is a perfectly valid type for this function, but it's actually not the best type. So that's fine. If this was an exam, I'd give you a point for that. But if I wanted the best type for this function, it's actually polymorphic, because if you look at the definition for the function, this says nothing about taking integers as the elements of the list. It could work for a list of any old thing. So in fact, this is a polymorphic function. So second, the best type for it is to say it takes a list of anything and gives you back a single thing of the same type. So that's kind of 2 ticks for that one. They're both perfectly valid types for the function, but the second one, the polymorphic one, is better because it's the most general type that this function could have. I mean, the integer one is actually an instance of this. If we just say, oh, the variable a is int, then we get the other one. So let's now have a look at swap, and we'll do the same kind of game again here. And we'll look at a simple example, and then we'll work out what the type is. So with swap, let's try swapping a couple of numbers. So what swap does is you give it 2 things and it just flips them around. So it takes xy to yx. So if we give it a couple of numbers, it will just swap them. Oops. And we will get 2 and 1. But the function is more general than that. I've given it 2 things of the same type, 2 integers here, but you could swap things of different types, and that's perfectly valid. So I could say, for example, I want to swap an integer and a Boolean, and that's perfectly valid to do. The definition doesn't place any constraints on the kind of things that you could swap, so I could do that. Okay, so this is again basically telling you that swap is a polymorphic function. The definition for the swap function doesn't say anything about the type of the elements at all. It doesn't constrain them to be numbers, booleans, characters, or whatever. So we can kind of read off now the type for swap. What swap is going to do is it's going to take a pair of an A and a B thing, and the A and B could be different things, as in the second example here. Here we have an integer and a Boolean. And then what it's going to give me back is the opposite. It's going to give me a pair of a B and an A. So it's a polymorphic function that takes a pair as its input and gives a pair in the opposite order as its output. Again, nice and simple. So let's look at one more final example here. This is a function called pair. So the definition says the pair of 2 things, x and y, is simply you pair them up. So a simple example of this one would be, if I start a GHCI and I type this in, I could say, what happens if I pair the integer 1 and the Boolean value false? Well, I would simply get the integer 1 and the Boolean value false sitting in a little pair. Okay, so you can look at the definition for the function here. And again, think, there's nothing in the definition that says that this must take an integer and a Boolean. It could take anything and anything else, and it would pair them up. So again, it's going to be a polymorphic function, but it's also, note, a curried function, because we take the 2 parameters here, x and y, one at a time. We don't place brackets around them. We take the number 1 here, then we take the value false, and then we're returning down here the pair 1 and false. So it's going to be a curried function, which is also polymorphic. So it brings together many of the ideas we've learned about today. So the most general type for this function, and again, if you ask GHC to calculate the type for you, it will say it's a curried function that takes an A thing, and then separately a B thing, and then it's going to give you back a pair of A and B things. So again, it's a polymorphic function because we have type variables in the type, and it's a curried function because we're taking 2 parameters one at a time. We're taking an A thing, then a B thing, and then finally we're giving back a pair of A and B. So I'll leave the rest of the exercises today for you to have a go at yourself. So that's it for today. I will see you again next time.